Hello, everyone. It's John. So this is the video for your last post lab, the Solubility Products Post Lab. And I'll be working through really each of these and what you want to do for the calculation portion of this section. All right, so the first part is the standardization of the sodium thiosulfate. All right, so first you're given this equation, and I'm really just going to, I think the easiest way for me to do this is I'm going to be putting this on a blank page, right? And then I will just be doing one question at a time to make this as clear as possible. All right, so let me change the template here and post this question. Or not. So let me go ahead and grab that again. So this first question is really asking you to balance this, right? You want to balance the charges or you want to balance the charges, right, as well as the atoms in this equation. So for this first one, the way I'm going to start balancing this is really just looking at some of the atoms. First, I'm going to try not worrying about the charges and seeing if it works out. If not, right, then we're going to have to do a different method here. So I'm going to say that this has a coefficient of 1, the iodate. The reason I'm doing that is because I have a hydrogen here, right, and a free iodine here that I can always change the number of, right, versus an H and an oxygen in this water, right? They're coupled together, and then there's an iodine here. So if that is 1, then that means I must have 3 waters here, right? If I have 3 waters, I have 6 hydrogens. And now what is left is to balance the iodines, right? I could say this is 1 and this is 1, right? But we're not going to get the right answer. So if I said those are both 1, then I would get the atom balance right, but I would not get the charge balance correct. So this will not be the answer, but let me erase these. The way you can look at this is currently, right, on this left side, I have a charge of 5 plus, right? I have 6 positive 1 charges, and I have 1 negative 1 charge, right? So the total is plus 5 on this side. On the right side, I have this H2O, which is neutral, and the iodine is also neutral. And so there's a charge of 0. So I need a charge of negative 5 on the left, right, from the iodine specifically. That's the only thing I haven't calculated yet, right, in the charge. For this left side to be 0. So we started with 5 plus, right, after we balanced everything else. And I need 5 negative charges to balance that out to get it to 0. So if I have 5 iodines on the left, I'm going to have iodates. No, iodide. Sorry. So iodide, right? Just like chloride, bromide, iodide is going to be the I minus. Iodate is the IO3, and then iodine is the I2. So just some of the terminology I'm going to be using in this post lab quite a lot. All right, so that first one was balanced. For the second one, it's really going to be the same thing. I'm just going to write in here how this would balance out, right? If you end up just balancing the sulfurs first, right? If you just tentatively put like a 2 here, right, a 2 and a 2, you'll find that the charges do not balance out. Now, yeah, they won't balance out. Interestingly enough, right, you can see on this side, right, we have a higher negative charge than this side. Oops, no, I didn't. So higher negative charge if everything is just 1, right? On this side, this one has 2, this one has 3. And so you have to find a way to multiply each side, right, to get the appropriate charge. All right. Now, right, you could do an algebraic method. I won't do that here. I did that in the first discussion video. I believe it was the first or like maybe the second one for balancing things. But you could do a system of equations here or guess and check. So the system of equations probably take a little bit of work. I'm going to skip that here. All right, so now we can go to the next question, right, which it says, for each of your 3 trials, use the volume and molarity of potassium iodate to determine the number of moles of KiO3 in solution, right? So this one's actually pretty easy. Once you have your equation. So all right, so for question number 2, this is relatively easy, right? All you have to do is do a lot of conversion, right? Your molarity of your solution should have been 0.1 molar, right? And so this is from the experimental procedure, right? So what you can do is convert this into moles, right? The way you're going to do this is for each of your 3 trials, right? You're going to take your, and then let me, right over here, I'm going to write this as KiO3 molarity, right? You're going to take your KiO3, or potassium iodate molarity, and you're going to convert this into moles, right? How do you convert this into moles? You convert it into moles by the volume that you use, right, from your titration. So this is going to be times the volume used or dispersed. Remember, it's going to be in liters for this, right, for molarity. So make sure you multiply it by liters, right? Convert your milliliters. And let me actually change this unit to that. That way it ends up canceling out, right? This is going to be equal to the moles of KiO3. Now I'm going to start introducing some Roman numerals here, just so I can easily refer back to these. I'm not going to be plugging in numbers for a lot of these. First, I don't have actual data, and next, it's actually too difficult for me to generate decent sample data to look something like yours. There's too many factors with the activity coefficients and stuff later on that I just cannot reasonably do it with the amount of time I have. So I'm going to introduce here the Roman numeral 1. Now, why I'm doing this is I will tell you in later steps, right? You should have gotten this in step 1, right? And that's why I'm keeping these numerals here, or it's from wherever the number 1 is, right? So you calculate it at that step, you're going to go back to that step and then plug it in. So that is the point of this. So these will be for later reference, right? Just so you know where these came from, which part at least. All right, and that's it, right? That's how you calculate the moles. Next, it says for each of your 3 trials, use the number of moles of KiO3, potassium iodate, present in solution in the stoichiometric ratio between that and sodium thiosulfate to determine the number of moles of sodium thiosulfate in your solution. So we're going to just do some more conversions here. Now, something to keep in mind, right? And then you could write this as an overall reaction, right? Just kind of adding them together, crossing most of these eyes out, right? I'm not sure if that would technically be accurate because this is in 2 steps, right? So you'd have an overall reaction, but there's some other stuff that's going on, I believe, with the indicators. And so I'm not sure if that would be entirely accurate, so I won't. Now, all we're going to do is another stoichiometric ratio, right? So in this reaction, you're assuming that the potassium iodate is your limiting reactant, right? You're also assuming that your sodium sulfate is going to be your limiting reactant. So you're going to have plenty of iodide this I minus, to react with these, right? So that's why this ends up working out. All right, so if we start with 1 mole, actually, yeah, I don't know how many moles, but you start with some amount of moles, right, of KiO3. I'm putting that over 1. This is from step 1, right? We just calculated this. This is just how I'm going to be referring to it in these equations, right? So you know where to find them, right? I calculated it from that one, essentially. All right. Multiply this, right? We want to convert this into moles of sodium thiosulfate. Now, the sodium thiosulfate is in a 1-to-1 ratio with this ion, this S2O3 2 minus ion, right? So I'm just going to go ahead and convert it to that. Right, so for every mole of KiO3 that I have, right, I get 3. I'm going to convert to iodine first because I can't directly relate this iodate to I believe it's not sulfate, sulfide, I believe. Yeah, sulfide. So I'm going to convert this into moles of iodide. This is for every 1 mole of KiO3. This is from the reaction, right? I get 3 moles of iodine. The units will cancel out. I won't cancel it out because it's going to look too messy here. And then for every 3 moles of iodine, I get 6 moles of sulfide. Right. And then you could go ahead and convert this again, right? These are in a 1-to-1 ratio. So for every 1 mole of sulfide you get, right, you have 1 mole of sodium thiosulfide. Okay. Na2S2O3. Actually, sulfide is SO3, so it wouldn't be sulfide. Sorry, thiosulfate. All right. Now you're going to get moles of sodium thiosulfate. Right? And I'm going to denote this with a 2, like that. All right, now that you have your moles of sodium thiosulfate, right, we're going to go to the next question here. It says for each of your 3 trials, use the volume of sodium thiosulfate at the equivalence point and the number of moles of sodium thiosulfate present in solution to determine the molarity of your sodium thiosulfate solution. All right. So let me scroll down here. Like that. Something I also should note, right, is you used 5 milliliters for this if you followed the procedure. I mean, you could do, I guess, your own, as I kind of said, like you could do different ratios and stuff, but if you followed what it said, you use 5 milliliters. All right, now all we have to do is, again, do a calculation here. So it says use the volume at the equivalence points and the number of moles to determine the molarity, right? The molarity of this solution, sodium thiosulfate solution, is equal to the moles of sodium thiosulfate that you got from step 2 over the volume dispersed. And I'm actually going to change the word here. Volume used, I think, is better. So this is going to be volume dispersed. In liters. Right, this is what you got from your burette readings, right? Just the final minus initial. So make sure to convert your milliliters. All right, next, number 5, it says, what is the average molarity, standard deviation, and 90% confidence limit of the Na2 sodium thiosulfate solution based on your 3 trials, right? So for this one, and I should refer to this as 3, by the way, as a reference. Right, so for the first part of this, right, your average is just your molarity values, right? Your 3 molarity values. Summed up. You get these from number 3. You're dividing it by 3, right? That's not that hard. What is the standard deviation? Right, so the standard deviation, now I'm actually going to do this. I'm going to call this M bar, just to make my life a little bit easier for this next part. All right, so for the standard deviation, you're going to take the square root, right? And you're going to sum up all the trials, except it's a little different. You're summing up each, we did this in the first lab, right? Where you take each trial value, you subtract the average from it, and you square it. So I'm going to call this molarity. Actually, I'll just do it like this. So trial 1 molarity, right, minus the average squared plus trial 2 molarity minus the average squared plus trial 3 molarity minus the average squared. And this is over 2, right? It's going to be 3 minus 1. So your number of trials minus 1. Then that is your standard deviation. All right, and then for the 90% confidence limit, we did this in, I believe it was the first discussion or first lab or something, right? I should write this as confidence limit instead. All right, but the formula is going to be your T critical, which in this case, let me double check. It's going to be 2.92 times the standard deviation over the square root of your n trials, n number of trials, which is going to be 3 in this case. All right, and then that's it for this first part. All right, next it says you're calculating the solubility of calcium iodate in pure water. So in your titration of saturated calcium iodate solution in pure water, what volume of standard sodium thiosulfate was required to reach the end point? Right, this. Let me go, oops, I need another sheet here. All you have to do is write this down. This is, I'm going to denote this with something. Na2SO3 volume. I'm going to denote this as 4 because we're going to have to refer to it later. All right. This is just from your data. All right. Next, you want to use the volume, right, of your molarity and your molarity, right, of your standardized Na2S2O3 to determine the moles dispensed at the equivalence point, right? So you figured out your moles of, your molarity of this solution, right, for the last one, question 4. So I've referred to this as 3. I will be doing so here, right? We have the Na2 SO3 molarity. Yeah, this is in units of moles over liters. I'm not going to write it like that. Just because like the units will cancel out, right? But we did leave it in molarity for step 3, and I don't want you to be confused on where you're looking for this. And then, so it's sodium thiosulfate times the sodium thiosulfate solution dispensed, right? And that is from number 4. That's from your data, right? Make sure you convert it to liters. You will get everything wrong if you do not. So please do that. This will give you the moles of sodium thiosulfate. I'm going to denote this with a 5. Right, we'll go to the next one here. Now you want to use the number of moles and the stoichiometric ratio to determine how many moles of IO3, iodate, were present. Right, so we're going to refer back to the first equation, right? Really what you're doing is this, but backwards. So I'm going to go ahead and skip a step here. I'm going to skip the step where we convert to the iodide, right? Because these end up canceling out. Sorry, iodine. Because these end up canceling out. So for every 6 moles of sodium thiosulfate, you have 1 mole of potassium iodate, right? Or in this case, just iodate because it's not potassium iodate. So my apologies, I shouldn't have said that. It's just iodate. Let me post this. All right. So you're going to use the moles of Na2SO3, right? This is from step 5 times, and then we're just going to go ahead and convert this, right? So we said for every 6 moles of sodium thiosulfate, you get 1 mole of iodate being used. Again, in this equation, right, it's not actually sodium thiosulfate, right? You could go ahead and convert to sodium thiosulfate, right? It is in a 1-to-1 ratio, right? You can see here that there is 1 S2O3. I'm not going to do that. I feel like it's just redundant. So it just takes up more time writing. So I won't be doing that for the rest of this lab, just so you're aware. But right, this is not in the reaction, but it dissolves into this. I forgot a 2 here, which is in the reaction, right? It's in a 1, and it's in a 1-to-1 ratio. All right, so then you'll get the moles of iodate in solution. And I'm just going to keep going with the Roman numerals here. Then we'll go into step 4. It says use the molarity, number of moles of iodate, right? And the volume of calcium iodate in water to calculate the molarity of iodate. All right, so you're going to use your moles of iodate from the last step. And you're going to divide this by the volume of calcium iodate, right? Again, you should have used 5 milliliters. Make sure you do this in liters though, right? You will get this wrong if you don't. And then you end up getting the molarity of, oops. One second. Oh, I forgot a 2 here. Right, but this will give you the molarity of your iodate. I forgot a minus here, right, in solution. And I'm going to call this Roman numeral 7. Right, the reason you don't have to convert this into something else where you may be asking, well, that's not the volume of just iodate. Right? There's 2 iodates in that instead of just 1, right? But you're looking at the moles of iodate that was in the solution, right, overall. And so all of these moles of iodate were in the 5 milliliters of that calcium iodate with the 2, right, iodate in there solution. And so you don't have to do some stoichiometric ratio because, again, you're looking at what's in the solution, not what is being formed in the solution, right? It's not breaking down, it's already broken down. So you should have used 5 milliliters, like I said, so just convert that to liters. All right, for the last part of number 5, they want you to calculate the solubility of calcium iodate. So they want you to figure out how much dissolved, essentially. You want to find so they give you the hint here, right? It says you want to figure out what the concentration of calcium is, essentially. So since you have to calculate the molarity of calcium right in here, because now this is actually due to the stoichiometric ratio, right? Because you have 2 iodates in every calcium iodate. You want to see just what the solubility of calcium is. So what is the concentration, right, of calcium in a saturated solution? Let's see. So it's going to be pretty easy from the last one here. You're going to find the molarity of calcium in your solution by taking this and dividing it by 2, right? You have 2 iodates in your solution for every calcium. So the concentration will be twice as high. Right? So if you want the concentration of calcium, you can just go ahead and divide this by 2. Oops, got that backwards. Molarity of calcium. And then you're good. This is going to be number 8. Right? So you'll have an actual number here. Then, and they actually do mention it here, right? The concentration of the calcium ion. It's based on for every 1 mole dissolving, right, as they say here. So that's why you want to find calcium, right? Because it's in a 2-to-1 ratio, or 1-to-1 ratio with calcium iodates, but calcium is in a 1-to-2 ratio with a iodate. All right, next one here. I believe we are on to part 3. So now we want to calculate the solubility product of calcium iodate in pure water based on concentration. Right, and so we're going to assume that the activity coefficients are equal to 1. We'll worry about that later. Yeah, so don't worry too much until later, right? Right now, you want to figure out an equation that describes the solubility product, right, in pure water in terms of the concentrations of calcium and iodate, right? So KSP is just the same as your K constant, right? It's going to be the concentration of iodate squared times the concentration of calcium. Right? This is because if you write the dissolution or the dissociation of calcium iodate, right, you get 2 iodate ions, right? That's why this is squared. And then you get 1 calcium ion here. So this is your KSP expression. That's it for number 1. Now it wants you to rewrite the equation, right, in terms of these solubilities. In terms of X, all right, so for this KSP, right, I'm going to just write these in. Now this calcium is the solubility, right? So that is X. The concentration of calcium is the solubility, is what we call it, right? This is going to be from number 8, right? So you should have that written down already somewhere. Now, what about this iodate, right? We said that the iodate, right, was twice as concentrated, right, as the calcium. So this is going to be a 2x here, right? It's twice as concentrated, so make sure you put the 2 there, right? It's not just x squared, it's going to be 2x quantity squared. If you go ahead and finish this out, you're going to get 4x cubed, right? Make sure you square the 2. Everything gets squared in there. Oops. All right, now on to the next one. We're just going to plug in the number So, oops. All we have to do is plug in the number here, right? And I should also note up here, X is equal to the concentration of calcium, right? That's all it is. And this is, again, this is from your step number 8 on the last page over here. All right, now we have this KSP, right? All we have to do is do 4 times the concentration of calcium. And I actually should have denoted all these concentrations with just brackets. I didn't think about it, but I will do that now. So 4 times the concentration of calcium 2 plus cubed. Again, this is from number 8. Now, something I should note is you actually don't even want to plug in the number for the last one, right? That's this one. So they're put in 2 different steps. All right, so once you do that, you just, oops, I guess we'll just leave it there. You should get your KSP, which I will denote with a 9, which is IX, I believe. Let me double check. That's correct. L is 50. All right. We can go on to the next one here. Right now, we're calculating the solubility product in water based on activity. So activity is essentially taking into account interactions between molecules, right? So in pure water, you just have the water, right? The dipole moment. Say oxygens are partially negative, right? The hydrogens are positive. You have intermolecular hydrogen bonding forces. And so that is what's dissolving, right? This ionic compound, essentially, right? They're attracted to those and then they end up dissolving. Now, if you have other things in the solution, right, such as other ions, I think we're using potassium iodide in this one, right? It's going to change, right, how much it dissolves, because if you have other ions in the solution that provide more interactions, right, more incentive for the molecule to dissolve, right, break apart in the solution, then they will. So now we're going to that's what really activity is it's taking into account these interactions, right, in the solution. So for this one, we're going to, for this first one, going to use equation 4 from the introduction. So I will go ahead and grab that really quick. I'll be right back. All right, so I'm back with this. Right, and so now we're going to go ahead and calculate mu, right, or the ionic strength, so of calcium iodate. So you want to use the concentration of each ion and the charge of each ion, right? That's pretty easy, right? You know the charges, right? The calcium is a 2 plus and the iodate is a 1 minus, right? So we're just going to follow this equation here, right? It's not too bad. Right, so mu is equal to, just remember that this just means you're adding them all up. I is just a placeholder, really, right? So for the first trial, or the first ion, first ion, right, concentration, first ion charge, second ion, right? You could have 100, you could have 1,000, you could have 1,000,000, right? So they put an I to just make it very general. Right, so 1/2 times the sum of the concentrations times their charge squared. So, or yeah, squared. All right, so the concentration of iodate, IO3, right? And then you're going to multiply this by -1 squared, right? That just ends up being 1. So not really a big thing to worry about. Now, this number is going to be number 7, from where you calculated it, plus the concentration of calcium. So, right, this was from number 8 times the charge, which is 2 squared. This is from your number 8, right? This is the X value that we just plugged in on the last problem. All right, I'm going to call this mu our step 10. Now it gets an X. So next it says to oh, my apologies. I went ahead. I guess I did not really read this fully. I remember it being a little different when I did this. We did the first 3 steps. So let me move this around really quick. So step 1 is just supposed to be, they want you to simplify it in terms of just one ion. So let me just go ahead and I'll just delete it. We'll go back over that one. So it was correct. I'm just gonna write all these out. So in case you need it. Mu is equal to 1/2 times, as I said, the concentration of, actually, I could have just used that since I left it generally. 1 second. Yeah, I don't need to get rid of that. All right. So we wrote it out. Then you're going to go ahead and write this in terms of X, or just the concentration of calcium, just so you don't have to plug in as many numbers, is essentially why they're having you do this. So X is the concentration of calcium, right? We know from the last one, right? Iodate is 2X, right? It's double the concentration of calcium. I'm not going to include the 1 because -1 squared is just 1. And then this is 2. Or, no, X. X times 4. Right? You go ahead and you simplify this, you get 1/2 times 6x, which is 3x. All right, now you can go ahead and plug everything in. That's what they want you to do in this 3rd step. So in this 3rd step, you're literally just plugging in the solubility of calcium, or solubility of calcium iodide, which is the concentration of calcium, right? And you got that in step 8. All right. Next, you're going to look at the table in the introduction to find the activity coefficients. I believe it means to say iodates, but we'll check the table here for the activity coefficient. All right, so if we go to table 1, now this is important. Please listen carefully for this, otherwise you might be confused. Let me just find the table here. There it is. All right, so if you're looking at this table, oh, awesome. I don't know why it went back, but give me 1 second to go back. All right. So if you look at this table, right, what you're going to do is round to the nearest tenths place for your decimal and pick the closest one. So I don't know because I don't have a number, right? But you're just going to pick what number is closest. So if your mu is 0.11, 0.12, you're going to go with these numbers, okay? Right. If it's 0.16, you're going to go with these. If it's 0.01, you're going to go with these, or 0.11, right? But round to the nearest tenths, right? And you should be okay. So if you're in the thousandths, double check the math. I believe it should be around the tenths place for this lab, or 100th place, sorry, for this lab. But yeah, so should be fine with rounding the nearest 100th place, the second decimal point, and then picking. But if you have one of these, just double check your math. And if everything works out, then just pick the one that's closest. So, all right. Again, you're just going to look at these. So the mu, right, the ionic strength for each of these is, let's see. Let me find it. We have calcium. All right, there it is. We have calcium, right, 2 plus. So let's say you have something like there, your calcium is 4.485, or if your mu is closest to 0.05, then you pick that one, right? And then also use your iodate, right? Make sure to pick whatever the closest one is, right? So whatever your mu is, pick the closest one. That's really it. All right, so when you pick your table, round to the nearest hundredths place after you calculate mu, as we did, right over here. And I should have called this X. So, and then pick your numbers, right? So again, just to tell you, right, these are the activity coefficients that we're going to be using in the next problem. So please just keep that in mind. If you don't do this correctly, you get confused, right? You won't know what to do for anything else. So these are the activity coefficients, right, based on mu. So this is not a mu column. This is activity coefficients, right? These are just ionic strength. These are all activity coefficients. These are all the gammas that we're going to be using. So please just keep that in mind. All right. So already note here, right? Using, or I'll say rounding mu to nearest, let's just round it to nearest thousandths place, right? But you should be fine rounding to nearest hundredths place. And again, mu is from number 10. It's from down here. We just calculated it. So rounding mu to the nearest thousandths place, look, not loot, at table. And then it was on page, let me just find it, page 94. On page 94 for activity coefficients of calcium 2 plus and calcium, or not, and iodate, right? That's wrong. That should be iodate. Right. I am going to denote some more Roman numerals here, right? Your gamma for the calcium, I want to keep this notation consistent. So we're going to use subscripts here. Right, so gamma of calcium 2 plus, right? This is equal to something, right? I'm going to call this xi, right? And then you're also going to want your activity coefficient of iodate, call this xii. And these are both from the table. And I forgot to put it. All right. On to the next one. It says, write an equation that describes the solubility product, KSP, of calcium iodate in pure water in terms of both the concentration and activity coefficients of both calcium and iodate. All right. So this one is similar. What we're going to do is really just write the KSP expression again, almost the same, except now you're including the activity coefficient. I suck at writing gammas. So like this times the concentration of calcium. Right, so it's basically what we had before, except now we have two things together. Now, why is that important? Maybe thinking, well, doesn't do anything, right? So it is important because we're going to be, for this iodate, squaring it as well. Right, the square applies to everything inside. So it applies to the iodate concentration as well as the activity coefficient. So you're going to get the activity coefficient, calcium, times the concentration of calcium, which we usually denote as X, right, from the previous ones, times the activity coefficient of iodate squared, do that, times the concentration of iodate squared. All right, now you just have to go ahead and plug in everything. Now they want you to do, I'm going to do 2 steps at once. I don't think it's really necessary to split these up. Maybe I should. Yeah, I'll do that because I was switching back from X to calcium concentration after. So I'll split these up. I think that makes it easier to follow for you guys. All right. We have KSP is equal to, now we're just writing it in terms of X, right? So we're same thing as we did before. X is the concentration of calcium. So these gamma coefficients are the same. All right, and if you simplify this, you end up getting, as we did before, 4x cubed, right, from the number 2 here, from number 8, times these two activity coefficients. And then you're just going to go ahead and plug in the numbers. Right, so the value you're going to get for these, so this is going to be KSP is equal to the activity coefficient of calcium times the activity coefficient of iodate, sorry, times the concentration of calcium to the third, sorry, times 4. Those are gammas, not 4s. So just remember that. Right now, your calcium, right? This is something you got from the table. This is Xi. This is from X double I, number 12. And then this was from number 8, I believe. Yes. All right. On to the next. So almost there. So calculating the solubility product, KSP, of calcium iodate in pure water based on activity. So, and I forgot to denote this. Oops. I need a number for this, right? So now this new KSP value, right? This is a different one. So before you assume that the activity coefficients were 1, this one is different. So this one is, I'm going to denote with a X triple I, right? Before we assume they were 1, but they are not 1. All right. Both concentration and activity. So what we're going to do is, we're on to this next one down here. So we're using the common ion effect. So we're calculating solubility, like the new solubility. All right. So we're going to be using the titration, right? Your last titration data for this one. So let me go to a new page here. Right, this is just from your data. So this is your volume of CaIO3 with potassium iodate, right? And this is from your data, right? You just look at your data that you recorded, right? From your burette measurement. Nope, sorry. That's for the sodium thiosulfate. This is from your data, right? You should have used 5 milliliters according to the procedure. All right. Yeah, that's it. So I'm going to denote this with an XIV, right? Just so we can keep referring back to these. Next, we have to use the volume and molarity, right, to determine the number of moles. So this is basically, I mean, this is exactly what you did in one of the previous questions, right? It's exactly the same as somewhere here as number 2 here, right? You have the molarity, you have the volume. then you're just multiplying it. So did I denote that with something? One second. Oh, okay. No, they were different. Problem is still the same though. So you're going to take your molarity of sodium thiosulfate and convert it into moles, right? By multiplying by the volume dispensed in liters. Make sure you convert. I'm not going to write it down. I will. And this was from somewhere in the first part. This was number 3. So this was from your third calculation, essentially, right? This is the last one the one just right above where you're just looking at your data. And then you're going to end up getting the moles of sodium thiosulfate. Notice how some of these units are the same. That's why I'm denoting it with these Roman numerals, right? Previously, we had moles of sodium thiosulfate, but the context was different. So this is XV. Then let's go on to the next one here. Going to use the number of moles, right, to determine how much iodate is in solution. All right. So we're just going to do the stoichiometric ratio we did before. All right, I'm actually just going to copy and paste it because it is exactly the same. Right. Different Roman numerals, but because of different contexts, but these are exactly the same. So this one, that was something new. Right, as I'm changing these new Roman numerals, right, just note that this is the moles of iodate, right, from both the calcium iodate and the potassium iodate. So this is now no longer, right, in a 1-to-1 ratio with how many moles of either calcium iodate, right, or potassium iodate were dissolved, right? This is the total moles of iodate, right? And you have 2 sources, right? So you can't just do some ratio and get, well, I have this much iodate, so I have, right, this much calcium. It doesn't work anymore. You got to do a little something extra here. So yeah, so this is the same though, the calculation at least. Context is different, as I said. So you want to calculate the molarity of iodate here. And again, this is literally the same, right? You just take your moles of iodate and you're going to divide it by the liters, or let's say volume of calcium iodate and, or I'll just say with to shorten this, with KiO3, right? You should have used 5 milliliters. Maybe you didn't. That's why I'm writing it generally here. Should have used 5 milliliters though, right? But make sure you do this in liters. I'm not going to write convert here, right? Just to remind any of you. I won't do it for the next one, if there is one though. All right, now you end up getting the molarity of iodate in this solution. Again, the contexts are different. So that's why I'm using these Roman numerals. So this is from, we'll say that this is number 17, right? This is from the last one that we just did. And then that last one's from the procedure. For this next one, we're going to go ahead and solve for the molarity, or using the molarity, right, of IO3 for the concentration of calcium. Now, you know, right, that there is 0.01 molar iodate from the potassium iodate solution, right? So that's going to affect our calculation. So what you're going to do is take your concentration of iodate, and let me write this out from step 3. Sorry, from step 18, calculation 18, I guess, whatever it is. Number 18, this thing up here. Or is that 17? No, that's 17. Sorry, 17. Can't read. You're going to take this. We're going to subtract 0.01 molar. Right? Now, this here, this is equal to the concentration of iodate from calcium iodate. Now, what I'm going to do is go ahead and divide this by 2, right? Because as we did before, we said that the concentration of calcium will be half of what the concentration of iodate is from calcium iodate. All right, so we are going to get concentration of calcium from this, right? Which is X, right? So that's what it is here. This I'm going to denote with XV triple I, and then we will go to the next one here. All right, on to the next section. All right, it says to write an equation that describes the solubility product in terms of, in pure water, in terms of the concentration of calcium and iodate. Let me get a new page. All right, so it's going to be the same thing here, right? As we had for, oh, we're not even including activity. So we're not even including activity here. So we'll do that next. All right, so the KSP here is the concentration, and we did this before. All right. This is exactly the same. Right, dissolves into calcium and iodate, 2 iodates. So this is the equilibrium product, right? Why don't we have anything on the bottom? These are the products, whereas the reactants, well, the reactant is a solid. We don't include that. All right, on to the next. They want you to rewrite this in terms of X, right, as we've been doing. You get KSP is equal to, where X is the concentration of calcium, All right, so this video will be a little discontinuous. I made a little bit of a mess up here. So you're going to use the entire concentration of the iodate, right? Not just the iodate from the calcium, from the calcium iodate, right? Kind of what you get on this top portion. You're going to use the concentration in the solution. So this here, this X, right? These are all just your calcium values. And so just to note, right, this is 2X plus 0.01. The 0.01 comes from the potassium iodate solution, right? That's already dissolved in before you saturate it with the calcium iodate. So that's that. And then over here, right, these labels are going to be X, V, I. This is the 18th label. All right. And that's it. All right. Now we're doing the next one where we're calculating mu. Oops. It's going to be the same as we did last time, except we are including the K, right? Because we have an extra ion here. So mu, we said was equal to 1/2 times the sum of all the concentrations times all their charges squared. Right. So in this case, the concentration, I think we're writing this generally. So this is going to be the concentration of potassium times 1 squared, right? Positive 1, wait, 1 squared, just times 1. No, it is 1 squared. And then it simplifies to 1. Has a charge of positive 1 times the concentration of calcium times 2 squared plus the concentration of iodate times negative 1 squared. And then they want you to write it in terms of X. All right. Now keep in mind, right, this iodate is all the iodate in the solution. So just keep that in mind, right? We already calculated it, so I don't see any reason why not to use it. So we'll do it. Right, you could just use the calcium. I think it's just going to simplify easier if we use the previous number that we had. So the concentration of calcium is 0.01. The 1 squared simplifies to 1. I'm not going to write it in. The calcium ends up being X, 4X. And then the iodate, I'm just going to denote that as the concentration of iodate. Right, this is some number, oops, that you got from, why didn't it move back? Okay, 1 second. So some number that you got back here, right? It is over here. So that is from step 17 or whatever, label 17. It's not equation at 17. We have a few more than that. So and that's it. And then you can simplify this into this. No, maybe it is easier just to use the concentration of calcium. So you don't have to plug in as many numbers. They will give you the exact same answer though. So I'm instead just going to write this as a 0.01 plus 2x as they gave us. So then this ends up being 0.02 plus 6x, which is 0.01 plus 3x. And that's it. Yeah, so that looks nicer. Easier to plug into your calculator too. Nope. Then you're going to go ahead and plug in your x. This is the same thing. So you're just plugging in the concentration of calcium for your x, right, that you got from step or label 18. So mu is equal to 0.01 plus 3 times the concentration of calcium, right? This was from your 18th label. All right. Last section. Now, did I copy the wrong thing? I did. Copy the wrong thing, but it's still going to be what we did before. Can I delete it? Where is it? Oh no, I didn't. Okay, I did copy the right thing. So we're not on the last portion yet. Not quite yet. All right, now you are going to do the exact same thing that we did for the last solution. Mu, this mu, I'm going to label this as x by x. So for 19, and I'm just going to copy what I said before. So rounding mu, right, this mu that we just calculated to the nearest thousands place. Look at the table on page 94 for the activity coefficients of calcium and iodate. Yeah, it's going to be literally the same thing here. Not color. Copy and paste. Let me just go ahead and change these labels. This will be XX and this will be XXI. What happened? Give me 1 second. All right, just got a little lost on where I was. So all you have to do here is we're just going to plug it into KSP. All right, so the KSP expression, the general KSP expression, I'm going to do all these at once, just so I don't have to copy and paste so much. The general KSP expression is the calcium activity coefficient times the concentration of calcium, right? We did this before. You are going to get the exact same thing. These are both squared, just keep that in mind. If I write this in terms of x, we're going to get this. I'm putting the 2 up here just so you, or parentheses, just so you keep in mind that it's squared. I remember the concentration of iodide. This is just the concentration of iodide from the calcium iodide. Oops. So the concentration of iodide is going to be okay. If I miss any edits, I won't miss any edits. Pause. All right, so this KSP expression is going to be what we did before. So this is the activity coefficient of calcium times the concentration of calcium. It's exactly the same expression times the activity coefficient of iodate times the concentration of iodate. This is all squared. So that is squared and that is squared. Now, to note, right, the concentration of iodate is everything in the solution, not just what was produced by the calcium iodate. So calcium iodate coefficient, right? If we write this in terms of X now, that is an X for the concentration of calcium, right? That's just how we're defining it. And then the concentration of iodate, is going to be 0.01 plus 2x squared. If you go ahead and simplify this, it's going to simplify to what we had on the last page, which is going to be this, except we have these 2 coefficients out here, right? Just make sure to include those. So I'm going to just write it all together right now. And then you can go ahead and replace the X with your concentration of calcium. Figure out my minuses. And I forgot to make that a square. All right, and you would plug that into your calculator. So this KSP, I'm going to denote this with an XXII. These gammas, right, are what you got before. This is your XX label, and this is your XXI label. This is going to be I messed up the label here again. This is going to be somewhere over here. XVI. Okay. So 18. This is your 18th label. All right. That's it for this one. So now that we figured out the KSP, right, using the activity coefficients, now you're going to one second. I think I actually may have copied the wrong thing here. No, they're the same thing. The numbers are a bit wrong. It's 5, 6, and 7. In this case, it's 4, 5, and 6. So, or no, it's still 5, 6, and 7. All right, so this is the last post lab video. I hope it helps. All right, so please study for your final. I will see you in discussion this week, or if you're in my class. Also, just best of luck in the future. It was great working with you this past semester in the lab and during discussions. So I wish you all the best. Hope this helps, and I will see you in discussion or on final exam day. So enjoy your week.